This is why brute force recursion fails on long strings. The exponential nightmare on the top shows how trying every possible cut creates a combinatorial explosion. The 2D matrix on the bottom handles the same data by solving the problem once. To achieve that efficiency, we use interval dynamic programming. The core idea is simple. Stop rereading the string and start looking up past computations. Look at the word CEC. To determine if it's a palindrome, we check the outer C's first. If they match, we only need to know if the middle part is also a palindrome. Since E is a single letter, it's a palindrome by default. Because the outer C's match and that inner E is already validated, the whole sequence is confirmed. By treating these strings like nested Russian dolls, we transform a complex search into an instant lookup. We'll use the string racecar-fox to build our solution. We need two tools, a 2D matrix to store palindrome states and a 1D array to track the minimum cuts required. We start with the base cases. For 1 or 2 letter substrings, the distance is so small that there is no inner part to check. This check prevents the algorithm from looking for data that would be out of bounds. Now, when we evaluate the prefix racecar, the matrix does the heavy lifting. We see the outer R's match, and a quick lookup of the ACAC cell tells us the middle is already a validated palindrome. This caching system means we never have to rescan the middle of a substring. The check for any range now takes constant time. Once the matrix validates racecar, the algorithm looks at our cuts array. It traces from the matrix down to the first index and records a 0. That 0 represents the number of cuts needed before this palindrome. Since racecar starts at the beginning of the string, no cuts are required. Moving to the next character, we identify F as its own isolated one-letter palindrome. Pause the video for a moment. Based on what we've solved so far, how many total cuts are needed for the prefix racercarf? The answer is 1. The algorithm looks at the cuts needed right before F, which was 0, and adds 1 cut to account for this new segment. By updating the cuts array while we fill the matrix, we integrate the verification and the optimization into a single traversal of the string. In C++, this logic lives inside a nested loop. The outer loop expands the substring, while the inner loop checks every possible split point. This specific line executes the lookback we just visualized. It checks the minimum cuts from the previous substring and adds 1. If the palindrome starts at index 0, the ternary operator keeps the cut count at 0, preventing a negative index search. To summarize, we use a 2D matrix for O1 palindrome checks and a 1D array to store the optimal cuts. Together, they bring the total complexity down to O of n squared. Understanding these state transitions allows you to optimize complex string problems without falling into the recursion trap. Follow for the next daily lesson.